In this lecture file, we'll look at Chapter 1 of Mapping Our Changing World, Introduction to GIS Science and Technology. The objectives of the chapter are to identify geographic data and what makes location-based data special, to explain the qualities of a map and what separates maps from other graphics, to recognize the sources of geographic data, and to describe the kinds of questions that GIS can help us answer. First of all, I wanted to introduce the concept of geographic information science, which I know was highlighted in one of the previous lecture files as well. This is the theory, use, and application of geographic information systems and databases to answer spatial questions. And this should be differentiated from geographic information systems, which is a computer system that processes geographic data and maps. In the chapter, the textbook identifies the 2003 statement by the U.S. Department of Labor, which recognized geospatial technology as a high-growth industry. This came out of the emergence of geospatial technology in the late 20th century. The link that is there on the page is something that you may want to take a look at if you want to see the tools and some of the information about the geospatial workforce and starting a geospatial career at the Department of Labor in the Employment and Training Administration. The link to this website is available in Blackboard under the lecture file for Units 3-4. So just next to where this file rests. You can click on the link and go from there. And as part of the growth of geospatial technology and the related fields, one of the things that emerged was the need for a definition, because all these technologies were coming out at the same time, and there was an abundance of spatial data emerging in the late 20th century. And so there needed to be some definition of this, because one of the big questions people couldn't answer was, well, what exactly does a geospatial practitioner need to do? So here's the industry definition. The geospatial industry acquires, integrates, manages, analyzes, maps, distributes, and uses geographic, temporal, and spatial information and knowledge. Pretty broad-based definition that's meant to capture all these different technologies and the theories behind them. And this came from the Geospatial Information and Technology Association and the Association of American Geographers. So the industry includes basic and applied research, technology development, education, and applications to address the planning, decision-making, and operational needs of people and organizations of all types. The 2000 census consensus definition came from these two organizations, and it reflects a coming of age of the field of study and the career field in a way. As was noted in one of the previous lectures, in 2010, the U.S. Department of Labor released the Geospatial Technology Competency Model, which kind of follows on the heels of this definition and effort to sort of better define what the industry is all about. The Department of Labor recognizes 10 geospatial occupations, which include surveyors, surveying technicians, surveying and mapping technicians, cartographers and photogrammetrists, geospatial information scientists and technologists, geographic information systems technicians, remote sensing scientists and technologists, remote sensing technicians, precision agriculture technicians, and geodetic surveyors. As we move through the course, you will get a better idea of what these different jobs mean. In several cases, they will feature fairly prominently in terms of the kinds of geographic information systems work that you'll be doing. And if you take more GIS courses beyond this one, you'll find out a great deal more about these fields. Multiple occupations also use geospatial technology. So these would be people who work in related fields, but may not technically be a GIS specialist or a technician or someone who identifies GIS as their main kind of task within their field. This is part of our vision with our certificate program, is that we are attempting to serve students who are going into these kinds of fields like public health and urban and regional planning and environmental management and energy and public safety and so on. And basically any profession where location matters and location technologies are important could be of interest to someone with a GIS. This chart is also included in your textbook, and it shows a couple of different things in terms of the future occupational outlook for the geospatial industry from the period 2010 to 2020. First of all, as of 2010, it shows the numbers of surveyors, surveying and mapping technicians, cartographers, and geographers employed in the U.S. job sector. And that's in the bars that are in blue. And then the green bars are the median annual salaries. and then the magenta looking color is the expected job growth, which you would read over on the percentage table over there to the right. So as you can see, in all of these job areas, the outlook is quite good in terms of expected job growth. It's important to think about the meaning of the term data overall. And so when we speak of data, we mean measured values that reflect phenomena or characteristics about phenomena. We typically look at data from the perspective of different variables, and a variable is a factor that may assume any value or set of values. For example, population per county. So the population itself would be the variable. An attribute is a synonym for a variable, and that's frequently used in GIS. And in ArcGIS, you'll notice, and you may have already noticed, that we have something called attribute tables. And attribute tables essentially put together the geographic area with the non-spatial data. Information overall is data that has been collected to answer a specific question. Within the world of geography and geographic data, we're talking here about data that include a reference to location on the Earth together with some non-spatial attributes. So geographic data, we typically are looking at the spatial aspects, so location is the spatial data, together with some non-spatial attributes, which makes the data actually usable. Geographic data are continuous and they're spatially dependent, and this means that even though individual features can be defined, all locations are connected across space. And when we say spatially dependent, for now, we'll just leave this to the concept that spatial location matters. So here's an example of non-geographic data. So this information can be represented visually through a graph or a chart, but it cannot be mapped as it is here since it lacks location information and does not have geographic data. So for example, the ID is the incident number or the number for the particular row in this case, most likely. Type is, in this case, related to some kind of emergency response, patrol, interceptor, ambulance, and description is just a description of what was involved. There's nothing in that can be mapped. When we add geographic data, in this case, XY coordinates, that is latitude and longitude, the information then can be represented visually by making a map as well. So you have to have that geographic element to the data in order to make a map. And what we can do with GIS is take non-spatial data, non-geographic data, and add location to it, and then be able to make a map. So geographic data are generalized according to scale. And again, the concept of map scale is the proportion between the distance on a map and the corresponding distance on the ground. And when we zoom into a map, map scale becomes larger. When we zoom out, map. This is an example of a smaller scale map, in this case, a view from Google Maps with the satellite view turned on of Michigan's northern lower peninsula. The next slide shows a larger scale map with more detail in the area outlined on this particular map in yellow. So in this case, we can see we've zoomed in this case, to Sleeping Bear Dunes National Lakeshore along Lake Michigan. And so this is the larger scale. The smaller scale map is a more generalized view of the region. And when we generalize maps, this means we're reducing and simplifying features on the Earth's surface in order to depict an area on a map. This map has less generalization, it's more zoomed in, it's a larger scale map, and most larger scale maps have less map generalization and include more details about the area being mapped. When we do GIS and we look at geographic information science, it's important to remember that we're fundamentally interested in spatial relationships. This gets us to the first law of geography, which is that everything is related to everything else, but near things are more related than distant things. And this came from Waldo Tobler in 1970. Geographic science asks this question: how alike are things in relation to their proximity? Geographic maps are abstractions of the world we live in and phenomenon on, within, or above its surface. Historically, maps were thought of as two-dimensional representations of the Earth's surface or a portion of it. We can contrast that with a globe, which is a three-dimensional representation of the Earth's surface or a portion of it. And again, a representation is a model or a simplified version of reality. And keep in mind that cartographic maps are a subset of geographic maps. So you can find more about this in Lecture 3, which is on map types. This is one of the diagrams that is that's in Chapter 1, and it's also one of the topics in the discussion forum for weeks 3 and 4. And it shows us different versions of diagrams that may or may not be maps. And so one of your tasks is to analyze and think about these and what it is that makes something a cartographic map, a geographic map, a mental map, and so on, and be able to discuss that in the discussion area. When we map out geographic data, we typically have two types of data collection. One is directly collected geographic data, and the other is remotely sensed geographic data. Directly collected data are generated at the source of the phenomena being measured, such as temperature measurements, elevations that are recorded at the site, the position of a grizzly bear equipped with a GPS-enabled collar, survey data from the U.S. Census, or observation data such as the Audubon Society's annual Christmas bird count, which they do all over the world. Remotely sensed geographic data are measured from remote distances without any direct contact with the phenomena or a need to visit the locations of interest, such as satellite images, aerial imagery, LiDAR, and radar. LiDAR, by the way, is a technology that is used from an aircraft sensor to determine elevations. No one is on the ground at the site when that data is taken to determine those elevations. It's done remotely, whereas the other option, direct observation, is a different way that you could collect elevation data. The chapter concludes with some questions about space, attributes, time, multiple geographic entities, attribute relationships, and temporal relationships. And one of the things I want you to think about as you kind of look at that list is, first of all, how broad this field is potentially, but how it is kind of wedded together with the geographic methods that geographic information science kind of brings to our table. And so rather than think about a million different examples of each one of these questions, I want you to just think about the broad nature of spatial analysis and spatial thinking, and then the need for methods that help us to make use of the potential for spatial analysis. And that concludes the lecture on Chapter 1.